It's working okay? Yeah, okay. Okay, thanks everyone for coming tonight. So tonight we're talking about Tasmanian search for exoplanets, and we've got Thomas Plunkett here from UTAS. He's a PhD candidate, and I need to get in front of this camera too, because we're live streaming this tonight. And so Thomas is a PhD candidate at the University of Tasmania, working mainly on the discovery of exoplanets using the UTAS optical telescopes at Green Hill Observatory. You've probably seen that up in the Midlands. There's a sign saying better go up to Bisditier, just before Oaklands. So that's where the Green Hill Observatory is, and we hope to go there one day for an outing. So he did his undergraduate degree in UTAS with his honours thesis relating to adaptive optics, following up planetary microlensing events with the Keck telescope in Hawaii. The start of his current research project focused on the setup of the new Harlington 50 centimetre telescope at Bisditier, developing code for processing data and performing photometry. He's now transitioned to validating transiting planet candidates alerted by the Transiting Exoplanet Survey Satellite, or TESS, mission. So I introduce Thomas. Welcome, Thomas.
Thank you so much. Well, hello everyone. Thank you so much for being here tonight. And thank you to the AST for inviting me to give this talk. I'm really excited to share some of the work I've been doing in my PhD project, starting a new program called TASI, a Tasmanian search for inclined exoplanets. So before we get into anything, what is an exoplanet? So an exoplanet is any planet that is not orbiting the sun. So that includes planets orbiting other stars in the Milky Way or even other galaxies, as well as planets just on their lonesome drifting through space, something we call a rogue planet. So since the early 90s, we've discovered nearly 6,000 of these exoplanets all across the galaxy, ranging in sizes from Jupiter down to below Earth size. But you might be thinking, why do we even care? Why do we do this in the first place? Well, there's a couple different reasons. The first thing is we actually don't understand how planets form very well. We have sort of the broad scale brushstrokes, but we only really had one system to study up until the 90s, and that was our solar system. And if you've ever done any statistics, you know that a sample size of 1, or a sample size of 8, I guess, is not really great number statistics for when you're trying to work out how things work. So that's the main reason. We find these planetary systems out there at various stages of their evolution, maybe just born, close to death, and everything in between. And then we can start to build this sample to say how planets form and how they evolve over time. Linked to this is understanding if our solar system is unique. So far, it's the only system that we know of that has life. And maybe that's because there's something special about the solar system. There are many other reasons that you've probably heard of. Maybe there are civilizations out there and they just don't want us to find them. But one of the main reasons that we do this work is to understand if there's something about the planets, where they are, the types of planets, that makes us special and has allowed us to develop intelligent life. More pragmatically, in the next hundreds of years, we're going to start running out of critical resources here on Earth. We're going to need to find new places to search for these, and one of the things we do in planetary science is understand the sort of distribution of resources in the solar system. So maybe we'll have to go out and mine asteroids or go to other planets even to find these resources in future. And finally, it's just a really cool thing to do. There are really weird exoplanets out there that are just completely alien to our experience here in the solar system. There's planets where there's diamonds raining from the sky, or there's planets that are so close to their sun that they're going around in less than a day. So they're celebrating New Year's Eve every single day, probably have a massive hangover perpetually. So I find that this topic is really good for encouraging people to go into STEM as well. So that's another reason that we do this. Right, so I've given you my spiel. Hopefully I've convinced you that's something worth listening to for the next 20, 30 minutes. Now let's move on to a just quick recap of the solar system. Because a lot of the ways that we understand exoplanets are through the context of the solar system, and vice versa. We use the exoplanets we find to understand the solar system as well. So we'll start with the planets closest to the sun. We've got Mercury on the top left, Venus top right, Earth and Mars. And these are the rocky planets or the terrestrial planets. Now I've listed some key parameters here on the side, and I'll explain what these mean if you haven't seen this notation before. So when you see something like R Earth or M Earth, that's just saying, put it in perspective of the size and the mass of Earth. Because the human brain is not wired to deal with hundreds of thousands, hundreds of millions even of kilograms or kilometers. So let's just contextualize everything in the size and mass of the Earth. So terrestrial planets range from 0.4 to 1 times the size of the Earth. We also use a weird unit for distance called the astronomical unit, which is the AU. And that's just the average distance between the sun and the Earth throughout the year. So if that's less than 1, it's closer than the Earth. If it's greater than 1, it's outwards from Earth. And maybe the most important thing that I've listed is this bulk density. So density is just how much mass you have squished into a volume of space. The higher that number is, the rockier the planet is. Just remember that. So we're going to move outwards into the solar system to the gas giants. So we've got Jupiter, the largest and most massive planet in the solar system. And we've got Saturn, which I personally think is the best planet in the solar system. It's got beautiful naked eye rings, cool hexagonal polar storm, hundreds of moons. Maybe they have life too, we don't know, but it's just a really cool place in the solar system. Now, you'll note that they're much larger than the Earth, ranging from about 9 to 11 times the radius of the Earth. Definitely a lot more massive, further out in the solar system as well. But the main thing to note is that these bulk densities are really, really low. So 0.7 to 1.3. Fun fact is, if we had a bathtub the size of Saturn, and we could ignore the effects of gravity and other issues, if you put Saturn in a bathtub of water, it would actually float because its density is lower than that of water, which is 1. All right, so moving outwards even further, we're getting to the ice giants. So we've got Uranus, which is the pale blue, and then Neptune on the right. So once again, larger than Earth, more massive than Earth, but not as big as the gas giant planets. Now, you can also note that the bulk densities are slightly larger than the gas giants, and that's just because at these distances from the sun, it's so cold that ice can start to form in the atmospheres of these planets. So things like water ice and methane. And that's actually the reason that you see these as blue, is because of methane ice. All right, so now we're moving to the last bits of the solar system, basically the leftovers of the planet formation process. So we've got the asteroid belt, so that's between Mars and Jupiter, hundreds of millions of just rocks floating through space, basically. Then we have the Kuiper belt and the Oort cloud, which are big puffy snowballs out past where Neptune orbits. And then we have dwarf planets like poor Pluto on the right here with its moon Charon. So that is the solar system. That's your primary school to high school level recap. Now let's move on to the main topic today, which is exoplanet discovery. So as I told you, since the early 90s, we've discovered nearly 6,000 of these exoplanets. And this has relied on multiple different methods to detect and characterize them. So I'm going to bring you through those today. Before we start with that though, I just want to highlight the very first few significant discoveries in the exoplanet field. So the very first planetary system we found outside of the solar system was around something called a pulsar. And a pulsar is a dead star that is rapidly rotating, and it gives off these periodic radio signals. They're so periodic that you can actually use them as clocks. They're basically the universe's clocks. So these two gentlemen here were using the Arecibo radio telescope and studying this pulsar with the telephone number shown there. And what they discovered was there were deviations in the timings that they were seeing from this pulsar. They expected to be, every few milliseconds you would see the signal, but there were slight delays or slight advances in the period of the signals they were seeing. And the only way they could explain this was if there were two Earth-ish sized planets orbiting around this dead star and pulling on the star itself and causing its rotation to slow or speed up. So that was the very first planetary system discovered. Then we move to maybe the more interesting one, because the last one, it's around a dead star. We probably won't find life there. It's not a great environment. There's a lot of radiation. This was the first time we found a planet that's familiar to us, like Jupiter, around a solar type star. So a solar type star just means something similar to the sun. And what they found was that there was a Jupiter-sized planet, but very different to the Jupiter that we know. And the reason for this was Jupiter has an orbit of a few years compared to the Earth. So Earth is 365 days. This was under 10 days. So it was extremely close to its host star, something we call a hot Jupiter. And our theories for planet formation cannot explain how this planet got there, or they couldn't at the time, because we just don't expect things to form there because it's so hot, there's so much pressure and radiation, nothing should form. So this really just kicked off the interest in exoplanets, trying to understand how this could be and how it got there. All right, so now we're going to go into the four main methods that we're using nowadays to discover exoplanets. So the first one is probably the easiest to understand, and I think it's what everyone thinks you do when you're an exoplanet scientist. They think you just go to a telescope, you point it at the sky, you look through the eyepiece, and bam, there's your planet. But there's a problem with that. Planets are really faint, they're really small, and space is stupidly big. So that just combines together to make it almost impossible for us to resolve these planets with even telescopes, even the largest telescopes. But luckily, in some systems, we can do this. And here is an example of one system. So this is using data from the Keck telescope in Hawaii. It's got a 10-meter mirror. And it's technically a stitch together of a bunch of images over a span of nearly a decade. And what you can see is they've got this big black circle in the middle. That's what we call a coronagraph. So it's like a mask that you put over the star to block out the light so that you can see fainter things behind the star. And you can see these four dots slowly moving around that central star, and they're all planets. They're planets that are a lot bigger than Jupiter, and they're orbiting further out than Neptune. So currently, this method is only useful in the extremes. It can only find young planets that are really far from their stars and they're really, really big. So maybe not the best tool for finding planets similar to Earth. The next technique is called the Doppler or radial velocity technique, and it was the one that was used to find that Jupiter companion to a solar type star that I mentioned. Now, who in the room's heard of the Doppler effect before? Good. A few people haven't, so I'll just explain it. And it's best explained with analogy, or something that you might have experienced. So if you've ever been in your car or on the sidewalk and you see an ambulance coming and it's got its siren on, as the ambulance gets close to you, you hear the siren increase in pitch. It sounds like it's getting higher. And then as it moves away from you, it sounds like it's getting lower. And that's the Doppler effect. Basically what is happening is as the siren is moving, the waves, the sound waves coming from the siren, compress together, and that is interpreted by your ear as an increase in pitch. And then as it moves away, those sound waves get further spaced apart, decrease in pitch. So that's the Doppler effect. That's for sound waves. But in fact, light also behaves like a wave. So therefore, the Doppler effect also works for light. So in this technique, if you have a planet orbiting a star, they dance around each other around a central point called the barycenter. Now, if the planet is orbiting, or the system is orbiting in the right sort of inclination, so edge onto us, it's going to pull and push the star towards or away from us. So if you break up the light coming from that star into its components, you can actually see the light getting shifted. So as the star comes towards us, it gets bluer. and then as it moves away from us, it gets redder. And this is the radial velocity technique. So because this is a gravitational effect, we can find the mass of these planets with this method. The next one is called microlensing, and this is by far the most complicated and convoluted method, so I'll do my best to explain this. But the reason it's important is those last few methods each have biases in the types of planets they can see. So I told you that you need young, big, far away for the direct imaging. Radial velocity is best for finding things close to the star or really, really far away, but not really good at probing in the middle region. This is where microlensing comes in because it is sensitive to a really wide range of what we call parameter space, so just where the planet might be orbiting. So in microlensing, this is where it gets tricky. Einstein taught us in the early 1900s that anything with mass curves spacetime. And a consequence of this is things with mass can actually act like magnifying lenses. So if anyone has ever had a magnifying lens, they've held it up to the sun, you can direct the light to a point and increase its intensity. Maybe you've burnt something with this method before. Well, the same thing actually happens for starlight. If you've got a really far away background star, maybe in the center of the galaxy, and then something like another star or a planetary system, a black hole, basically anything with mass, travels in front of that background star and closely aligns with it, it will actually increase the brightness of the background star because it's acting like a magnifying lens. So I'll show you an example of what this looks like. We've got a planetary system on the top, so the red dot is a star, planet is going around that star. In the background, you've got this really distant, faraway background star, and as they come close together, you can see in the curve on the bottom, which is plotting the brightness as a function of time, there's a gradual increase, sort of like a bell curve shape. And then as it's going behind the planet, there's that extra little spike. So it will come through again in a second. So there we go, little spike. The planet is acting like a magnifying lens as well. And so in this method, we're able to measure the mass and the separation using just the light from that background star. So it's unique in that it doesn't rely on that closest star's light like the other methods. All right, so the final method to go through, and this is the easiest, I think, to explain, and also the most successful, and it's the most pertinent to the next section of the talk. So in the transit method, what happens is you've got a planet that's orbiting around its star, edge on to us as we're looking at it from Earth. And as that planet goes around its star, it crosses over it and blocks a little bit of the light. So it casts a shadow to us here on Earth. So this will happen periodically as the planet goes about its orbit, and we're able to actually measure the size of the planet with this method. And the reason for this is, if you imagine I was holding a light bulb, you put a marble in front of it, it's not going to block a lot of the light. You put your fist in front of it, you're going to block a lot more of the light. You put a basketball, most of the light. And that's basically just because you have an increase in the surface area. And the surface area is related to the radius, therefore we can get it from what we call the light curve. So this little dip represents, as the planet is passing in front of its star, what you would see from a telescope if you looked at the brightness of that star over time. So this method has found about 2/3 of the total exoplanet population so far. All right, so coming on to the last section of the talk, that's been all the intro. Now I'm going to talk about the work that I've been doing at the UTAS Green Hill Observatory in searching for more transiting exoplanets. So I've started a project called TASI, or the Tasmanian Search for Inclined Exoplanets. And I'll just note that inclined here means it's transiting. It has to have a high inclination of about 90 for us to see it transit. So that's just a bit of technical mumbo jumbo, but that was me trying to force the acronym. So. All right, so because the transit method has been so successful, NASA decided that they would launch a dedicated mission to use this technique to search for more exoplanets. So in 2018, TESS, the Transiting Exoplanet Survey Satellite, was launched, and it's currently an ongoing mission that is taking measurements across the whole sky. Every 27 days, it's scanning in single patches. So it looks at the single patch of the sky for 27 days, moves on to the next patch and the next, and repeats it over and over. And what they're doing is they're looking for those periodic dips in the brightness of stars in their field of view. Now, after doing some preliminary checks, these get announced to the community as something called a test object of interest. So they're basically saying, hello, we think we found a planet, but we need you to follow it up. And the reason that we need to do this is TESS has a really, really bad spatial resolution. It's got what we call a pixel scale of 21 arcseconds per pixel, and that's probably just a number that means nothing. So let me show you an example. So on the left, you've got a cutout from an image from the TESS telescope. And then on the right, you've got the exact same region in the sky, but with our telescope. You can just see how much TESS misses. There's just a bunch of things that blend together into a single pixel on the detector. And a consequence of this is it increases the likelihood of us getting it wrong, of claiming there's a planet where there's not. So this could be things like eclipsing binaries, which are stars orbiting stars, or it could be star spots, like the ones we get on the sun. All of these things can mimic planet signals and make us claim there are planets when there are not. So you need to do follow-up work with better telescopes, better might be the wrong word, higher resolution telescopes to rule these out as actually, whether or not they're actually planets. We also do it to improve the parameter accuracy, so get a better measure of the radius of the planet, and also to refine what we call the ephemeris. So that's just saying where exactly is the planet in its orbit at all times. And the reason we need to know this is probably best explained with a recent example I heard. Some people were using the Hubble Space Telescope to observe a transiting planet, but it hadn't been observed in 10 years. The problem with transiting planets is if you have any uncertainty on when the transit is going to happen, that just compounds and compounds and compounds over time. So you could say, I'm uncertain to maybe a few minutes to begin with, but if you don't observe it for 10 years, that can increase to days. So you have no idea where it is on its orbit, and these poor people burnt a whole bunch of Hubble time on a planet that wasn't actually visible at that point. So that is the reason that we need to do this work. We need to refine when this transit is going to happen if we want to make a proposal with bigger telescopes, basically. All right, so let me introduce you to the Green Hill Observatory. As Dallas was saying, it's in the Midlands. It's about an hour and 15 minutes from Hobart. We have two optical telescopes. We've got a 50 centimetre and we've got a 1.3 metre, which is currently under refurbishment. And then, you might know about that, the radio antenna on the side. The site has pretty average statistics. So seeing is just a number telling you how good your images are on average. It's a measure of the turbulence above the observatory, but don't worry about that. It's a pretty reasonable number for the type of observatory that it is. And we can observe for about 28 to 34% of nighttime hours. Now focusing in on the instrument that we actually used in this project. So this is the Harlington 50 centimetre telescope. It's a plane wave CDK 20-inch for all the it's got an Apogee Alta U42 deep cooling CCD, and it's mounted onto an Alcor Systems Nova 120 mount. So that has a really, really quick mount. It's 20 degrees per second slew rate if it wanted to be. The field of view is 27.2 square arc minutes, so nearly half a degree. And just for context, that's about the size of the full moon in the sky. And the limiting magnitude in about an hour of integration time is R equals 20. That's just a number telling you how faint you can see. The larger that number is, the fainter you get. So we're actually doing really well for the size of the telescope. All right, so we're on to the results section. Over the summer of 2023 to 2024, I observed 5 TOIs, so remember TESS objects of interest, that were flagged as planet candidates by the TESS team. So these are all really deep southern targets, which means no telescopes in the northern hemisphere can see these candidates. So in total, I took about 429 images, which equates to 16 hours of manual telescope time of me sitting on campus by my lonesome, which is a bit sad. And creepy possums. No, the possums are beautiful. We love the possums. So these are just cutouts of centered on the targets that we were looking at. Now, the next bits get a bit hairy. I'm going to sort of try and skim through some of the science, but I just thought it was important to sort of show what goes into the actual work that we do. I won't go into too much depth, so You can check your phones for 5 minutes if you're a bit worried about seeing some science, but I promise it won't be too painful. The first thing you need to do when you do a transit study is understand the type of stars that your planets are going around. And the reason for that is I kind of lied to you. You can't just measure the radius of a planet with this method. You actually get a measurement of the radius ratio between the planet and the star. So you need to know the radius of the star if you want to know the radius of the planet, and you also need to know its density for a couple of other reasons. So that was the first step. We need to know what type of star we're looking at. Now, I'll skim through this just to say that there were 3 independent methods that we used to get the mass, the radius, and the density of the star, and then we just fed this all into our modeling process to get the actual radius out. If you're interested in what this actually means, you can feel free to ask me at the end. Another thing we looked into was the kinematics. So kinematics just means looking at your star, where is it in the galaxy? So how far away? Where is it moving? What's its velocity? Now we have this awesome mission that was launched a few years ago now by the ESA, so the European Space Agency, called Gaia. And Gaia is doing this amazing job where it's mapping out the whole galaxy. It's telling us the very precise positions and velocities of stars across the entire galaxy. So it's been really, really revolutionary in astronomy. And as a consequence, we get to use its data, which is great. So we looked into the kinematics of these stars just to learn more about where they were, what their ages are like, and also if they belong to any associations or anything. The next bit was looking into the stellar activity. So you might know that the sun has an activity cycle of about 11 years, or technically it's 22 if you count it properly. But that corresponds to an increase or decrease in star spots or sunspots, and that correlates with the aurora activity we get, which we see particularly well from Tassie. So turns out stars, other than the sun, also have star spots. They also have activity cycles, and they can be a real pain in the ass to model. So you really need to account for any variability in your star if you want to recover these really small transit signals. Right, so that is finding out what types of stars we're looking at. We now need to actually say, are these planets or not? So once again, I won't dive into the nitty-gritty boring details. You can ask me if you're interested, but we have a variety of different methods that we use, including codes that we run, as well as different statistics that allow us to say whether something is a planet or not based on the data that we have. Sadly, 3 of these were not planets. They were either eclipsing binaries, so stars around stars, or stellar activity, so star spots, which was a bit of a bummer. You put in so much time observing something and then you get this result and you're a bit sad. But then you realize that you've got 2 systems that passed all the checks and they're probably planets. So let's now move on to doing the proper modeling. So I, once again, won't go into too much about this. We're using a code called Juliet, which is publicly available. Basically, you put in all the data from TESS, which is in the blue. You put all the data in from our telescope, which is in the red. And you do this modeling to figure out the radius of the planet, where it is, what's its orbit, things like that. So yeah, that's just an example of what it really looks like in practice to do this kind of work. And it spits out a whole bunch of estimates of all the parameters that we need. Okay, now onto the actual interesting bit. So come back from your phones if you were on them before. Now I'm going to talk about the actual results. So we've got 2 new short period giant planets that were discovered by Tasmanians, which is pretty cool. So they're 2 planets with periods less than 5 days. Just remember that Earth is 365 days. Mercury is 88 days. So these are really, really, really close to their stars. So the one on the top is sort of your typical hot Jupiter. That is like the one that was announced in '95 that I showed you, the Jupiter companion to solar type star, sort of similar to that. So it's about 1.4 times the radius of Jupiter. So pretty typical planet to find. The one on the left got us really, really excited though, because it's unique for a multitude of reasons. The first reason that makes it interesting is it's sitting in this region of the parameter space. So by the way, I'm plotting radius against the orbital period for planets, all the planets that we know under 10-day orbital period. So that's just what all these colored points are. They represent all the planets that we know of in this area of space. So you see this big gap in the center of this distribution. That is called the subjovian desert. And we don't find many planets there because they either get ripped apart if they're too close to their stars, or they slowly evaporate away their atmosphere and shrink down and shrink down. So we've found a planet that's either sitting on the edge or maybe within that subjovian desert, which is really weird in itself. The next reason it's interesting is it's a binary system. So we've got a central star with the planet around it, and then we've got a really distant background star that is also orbiting that system. Sort of think like Tatooine, but slightly different. And then the final reason it's interesting is it's got a low metallicity. In astronomy, we're a bit weird because we think of anything that's heavier than helium. Anything heavier than helium, we treat as a metal. And if you're a chemist in the room, you probably just threw up in your mouth because that's disgusting. That's not how the periodic table works. But if you look at the universe, it's mostly hydrogen and helium. So we just pretend everything else is metal. So this is a system that has really low metals. And that means we don't expect planets to actually form very well around these types of stars. There's not really enough material that is heavy enough to spawn the planet forming process. So it's very strange to find a large gas giant planet around this type of star. So all of this combined together to say, this is a really cool system, we should do more work on this, and we're hoping to do more mass and atmospheric studies in the future. All right, so you've lasted through my talk. I'm just coming to the end now, but I just want to mention some of the future goals that we have. So we're hoping to do another round of observing over the summer to find more planets. So Tassie Part 2, so stay tuned for some more planet discoveries from us. Also want to mention that we work on microlensing follow-up, so you might remember that method, magnifying lens on the star. We also do that too at the observatory, and there's a rich history of it at UTAS, which you can ask me about, or you might have heard of from Andrew Cole or John Philippe if he's ever given a talk here. We also work on stellar occultations. That's just more related to planetary solar system science. And the other goal is to hopefully finish the PhD at some point. I'm about just over the halfway mark now, so a year and a half to go, so wish me luck. So I'll come to the end of my talk. I just want to say that, yeah, if you want to get in contact with me, feel free to send me an email. I always love to talk about planets and astronomy more broadly. And I have submitted this paper to a scientific journal. I don't expect a lot of people go to Archive or PASA, but if you do, it will be there soon, hopefully. More interestingly, I'm hoping to send this to Martin George, who writes in the Mercury. I caught up with him in Canberra while I was at a conference, and he said he was really keen to write a story about this. So maybe keep your eyes peeled in the Mercury or on the Hive website at least. And I'll leave it there. Thank you so much for listening. Oh yes, feel free to ask any questions if you have. Yes.
The Triceratops appeared in your book. What was
You
the?
can ask questions.
Oh, sorry. Yes, just curious, Tom. The Triceratops. Why did you have that there?
Let's go back to Triceratops.
That was to keep us awake and notice things.
Yes, I was just keeping you sharp. Triceratops is a code that we use to test if something is a planet. So it fits models for eclipsing binaries and transits, various different scenarios, and gives you an estimate of how likely something is actually a planet. It's an acronym, but I can't remember for the life of me what it fully stands for. It's long and it's not obvious. Like I tried to make mine obvious. I think Tassie, I did all right. This one's pretty egregious. So if you're interested, go look it up because it's not good.
Okay, thank you.
Any other questions?
Uh,
Can I just get you to ask that again for people watching online? Sorry.
Do you get to name the planets that you've discovered?
in my brain, I do, but sadly not. They're named after the star that they're around, so it's kind of lame. Yes, so the official name would be TOI, Test Object of Interest 3097AB. So yeah, a bit sad about that. But Plunkett 1 and Plunkett 2 is the one name.
From
So the one that's the one of interest, the one that we're all excited about.
Yeah.
So could that be a rogue planet that's just sort of landed there and been captured, and that's why it's sitting there as opposed to actually developed in that particular area?
That is a really good question.
I listened.
Thank you.
Oh, no, no.
I think it would be, it's hard to say with current data is what I would say. There are other options for how it could have gotten there, whether that be it sort of cannibalized another planet and grew to a larger size that way. Not impossible, but you would also then expect maybe the stars would become unstable because you've got that big gravitational perturbation coming through. It's going to mess things up. So interesting question. I hadn't actually thought about too much. So I will have a more think.
So sticking with Blobby number one,
Yep.
Contrary to Bronwyn's suggestion of it being a rogue planet, it's odd that it's there, isn't it? We're not expecting it to be there, and yet it's interesting that a very early one was in the same sort of vein when we first started to discover them. So maybe there is it potentially that there are more there, and that what we think's odd isn't odd after all. So obviously more research is going to find that, well, you know, this is where these big blobby ones do appear.
Yeah, I will clarify that the first one that they found that I mentioned was within this distribution here. The closer you get is when it gets more rare. So they were probably at about 3 to 5 days. This is orbiting every roughly 1.2 days. But you're exactly right. We do see there are planets in here. And the one thing that might make us sure that we're not missing things is the methods we're using are really sensitive to these type of planets. The transit method and the radial velocity method are the best at finding planets in this range. So there's definitely more to find, but we have pretty reasonable guesses about how complete our surveys are, at least in this region. If you go any further out, you're absolutely right. We're missing a whole bunch of planets because these methods are just not sensitive to those regions of the parameter space. Yeah.
And you have some other close to zero. You have a red dot.
Yes, yes.
What does that translate into? How many hours?
Oh, okay. So let's see. We've got 1 day there. We've got 0 there. I believe. Am I on my log scale? No, actually, that's 0.5-ish days. I think the smallest we've found. I clipped it off because yeah, there's nothing really down there. The smallest we found is, I think, about 0.52-ish days. Yeah, yeah. It's a fast journey. For dear life, yeah, yeah. You also wouldn't want to be there. Yeah, I guess another thing to note while I'm here is the color of these dots corresponds to the temperature of the stars that the planets are orbiting. So things in orange, like the sun, things in red, much smaller than the sun. So this extreme example over here is quite a cool star. So being that close may not be super catastrophic for you, but then again, M dwarfs. Mm.
The other thing is the percentage of dots going into the blues lower. Is that because they're hard to detect?
Yes, yeah, no, that's exactly right. TESS, I think, saturates at mag 6 or 7 in visual. So yeah, the stars above this that are quite blue, they're really, really hot. They're also really, really bright because they're giant stars. And we just don't have a lot of surveys that are capable to look for planets around those types of stars. Yeah, just far too bright, destroys the sensor. Yeah.
Audience online.
Yeah, for sure.
Yep, we've got two online questions here. The first one is, has more than one planet been found around the star?
Yes, absolutely. You might have heard of the TRAPPIST-1 system before. So that's the first system that we found, well, one of the first, probably not the first, with 7 rocky type planets, so similar to Earth size. And this was really, really exciting, really interesting. So currently the James Webb Space Telescope, which you might have heard as well, is targeting in on that system because we want to know, are there atmospheres on these planets? Could they harbour life? Yeah, so definitely, yes.
And the second question is, can you tell if any of the hot Jupiters actually combust when they are in close orbits to their star?
That's a great question. They wouldn't combust, but they do, or maybe not while they're still held together, they wouldn't combust. But when they get too close, they get ripped apart. So if you move as a giant planet too far inwards, you're just going to be spaghettified, basically, by the star. That's because the gravity of the star and the gravity of planet of large planets is more extreme. There's more of an extreme interaction between the two of them. So not combusting while it's still held together, but maybe combusting as it's dragged onto the star when it reaches the end of its life.
I think we have one more from Bronwyn. Yeah.
I'm back. So are you able to tell the composition of the exoplanets and, terrestrial versus, I'm assuming given that
Yes.
close that they're obviously going to be terrestrial rather than, yes.
You raised an excellent point that I completely forgot to mention, which was a very critical point that I really missed. You know how I was yammering on about those bulk densities at the start? You were thinking, why is he talking about this? We don't care. Well, if you have the radial velocity technique and the transiting technique, you've got the radius and you've got the mass. That gives you density. So you can actually start to say, oh, if it's got a low density, it's probably gas. If it's high density, it's probably rock. But we can go even further than that with telescopes like JWST and do what we call transmission spectroscopy. So that's when you break up the light coming from the planet's atmosphere, technically from the star passing through the planet's atmosphere. And that tells you the chemical composition and the molecular composition. So yeah, we can explore it even further. We do know that, yeah, all of these are gas-type planets, and all of these are either super Earths, maybe pushing down to Earth in the extreme, or planets that aren't even in the solar system called mini-Neptunes. So they're, just imagine Neptune but smaller. And that might be because they started like Neptune and had their atmosphere completely evaporated.
So that's part of your PhD there, are you just detecting?
Yes, so in this study, we sadly didn't have access to any telescopes that could do the radial velocity. That's hopefully something we can do in the future. The next round, I'm currently putting in telescope proposals. The deadline is actually tomorrow, so might be working on that. Yeah, but we're putting in telescope proposals to do exactly that, get radial velocity on these targets as well, so that we can say, are they rocky or gas type planets?
Sorry, Thomas, just one down the back here, sorry.
The candidate you've got there, which is the low metallicity.
Yes.
Now, is the position in the Milky Way and the motion, is that consistent with a disk star or an old halo star?
I'm so glad you asked that question. It's tantalizingly probably a halo star. So if you remember me talking about kinematics, we're using that Gaia telescope, getting precise positions, velocities. We looked at this target, and the way that it is moving is kind of odd compared to the other targets. I think I've got a plot. So I didn't really explain this plot, but you're basically plotting the 3 components of its velocity throughout the galaxy. I can't remember the exact ordering of what directions, but you can see that all of these targets are on this side of the plot, and they're sort of lower down. And the low metallicity one is sitting out here. So when you do the analysis and you use the stuff from this paper that I've quoted there, it's possibly a thick disk or halo star. So for those that aren't familiar with galactic archaeology, Milky Way, think of it as a sombrero. You've got central bulgy sort of area, like a sphere. You've got a disk that goes around the galaxy, But then there's also another disk that extends upwards from that, what we call the thin disk. And this is a population of older stars. So we're finding something that is probably a bit older and has less time to grow and accumulate metals. So yeah, it was not enough evidence to conclusively say, but tantalizing hint. Yeah.
Richard?
To date, have we detected water?
We've detected water in gas giant planets, but not on a terrestrial planet yet. I don't believe. It's a lot harder on smaller planets. The larger planet kind of makes it easier to detect these things. But that's what we're hoping to do, push down further and further.
Thomas, I just want to mention that Stefan up the back there was part of the team that found some exoplanets at Mount Canopus.
Oh, awesome.
So you might like to have a chat to him
Yeah, absolutely.
later in the evening. And also, we had a presentation by another PhD candidate a few years ago, and she's now working in the United States for NASA.
Was that Katie?
Looking for exoplanets, yeah.
Yeah.
So do you have any dreams of joining them, or?
That's a loaded question. Yeah, I'm not sure. I won't get political about it, but I'm not sure if I want to move to the US currently. So I'm currently thinking about maybe closer to home, if possible.
I believe there's some in a European country looking for exoplanets. I'm in touch with a woman from California, and she went to a lecture yesterday about this team in Europe looking for exoplanets.
Oh, cool. Okay. Well, yeah, I'd love to learn more because on the job search soon enough, but yeah.
Are there any other questions?
You have an update on the 1.3?
You sure can.
We've been hearing about it for a few years now.
For context, the 1.3 meter is a cursed telescope. So that's the larger one here. It was the first one that was on the site. It's cursed for a multitude of reasons, and I'm actually not sure if I can share the specific details. I will just say that the mirror is going to be refurbished and it's been sent off to New Zealand. It's arrived. It's at the optics lab. They're currently working on it. So we expect to possibly get it back within a year, but that's touch wood, fingers crossed, every single toe. Because, yeah, it's been a saga. It's been almost
6 years?
At least 6 years since we've had problems with it. So, yeah. If you want the official history, you can come ask me. I just can't repeat it probably over the mic.
So are there any other questions? So I'd like to thank...
Oh, I think there was one more.
Okay.
Sorry.
Another online one.
It's not a question, it's more of a comment. Comment from Andrew Boyd is, Dr. Maddie Marshall from Wynyard works with the James Webb Telescope data and plans missions based in Canada now.
Wow, okay. That's awesome. I haven't heard of her before, so yeah, that's really cool to learn. I should, yeah, get in contact with her. It'd be great to have a chat.
Okay, so thanks for coming along tonight, Thomas, and we can see how you love chasing exoplanets. It's a passion of yours, and we'd like to give you a present before you go. So here's a bottle of wine.
Thank you very
from
much.
the astronomical.
Thank you so much.
So we hope you enjoy it.
Thank you so much for giving me the opportunity to give this talk. It's been really great, and yeah, thanks for listening.
Yeah.
Okay, so we're just going to stop and have a quick break. So we'll just give everybody online a chance to go and get a cup of tea, and we'll be coming back to you here,
You were the
Richard.
line of sight.
I sent out an email to all members today, just to let you know we're organising another barbecue at Campbelltown in January, so just check the email. come along if you can.
Sorry. Stole it.
Stick around, I've got a show for you.
Just one other thing. With before you have the break, we've got an observing night this Saturday at Mount Pleasant. Although it looks like it's going to rain, so.
We could contribute to the science,
Well,
you know what I
honestly,
mean?
you could. That's the thing.
Well, I think people
Yeah.
in society that would be really interested in,
Yeah.
you know, I don't know, going through data or I don't know.
And that's the thing.
Thank you,
You
Janice.
don't need a large telescope to do this. That's
Yeah, yeah.
So, I know a lot of people have almost similar sized telescopes to the one we're using, just in personal use. So,
Yeah,
it really is
Well, like I
possible.
said, well, maybe, you know, I mean, I know we're coming to a crazy
Don't you start. My name is Maximus. Yeah. Shh. I shouldn't have told you about that. I knew. Okay, folks. Sorry. Lights, camera, action. Thank you. All right. So tonight I'm going to do a little presentation on the summer sky. It's not my usual 1 month ahead. It's going to be pitched at January the 15th. So remembering, the difference between solar time and sidereal time, 4 minutes a day, half an hour a week. The stars will be, at the end of the month, will be rising 2 hours earlier than they were at the beginning of the month. So things will be slightly different when you look at this from what they are at the moment, obviously. So anyone recognise that? Apart from those who are die-hard photographers like yours, Troy? No? NGC 3576, does it ring a bell?
Oh, yes.
Oh, come on. Statue of Liberty Nebula.
Oh.
Now, this is the one I reworked from the original. You can all see the Statue of Liberty. There she is.
Oh, yeah, that's right.
Yeah. Okay. That's between the Southern Cross and IC268, Southern Pleiades, and sort of halfway along. Very pretty object. All right, now we'll get started. Sorry? Oh. Well, this is going to have all elements of all sorts of things in it tonight, even a bit of Halloween. My eyesight's not going well. What have I done there? Did I click the right thing? I think so. And no, it's all right. It's okay. It'll work. Oh, Jesse Gallagher, track it. If that's a Celestron power tank is rubbish. It is. They're terrible.
You look very young.
Yeah. Okay, so let's move on. Music aside, the northern sky. Remember, this is 15th of January. Has got some wonderful things in it. You can already see Jupiter on the ecliptic there. You can watch out Jupiter and look at the moons transiting. It's a wonderful thing. But what dominates the sky are certain constellations. The one I'm going to look at a little bit tonight in a bit more detail is Taurus, which we rarely talk about. But Taurus has got the most fascinating objects down here. Can you see these little patches? Yeah, and LDN. Right, let me tell you a bit about LDN before I go any further, because I'm going to refer to these. LDN means Lynds Dark Nebula. Now, you all heard of E.E. Barnard. Barnard, who discovered looked at mapped dark nebulae. This woman wiped him out completely and mapped 1,800, in excess of that. So she is by far the greater mapper of dark nebulae than E.E. Barnard was. But being a woman in the time she did that, of course, she got no real acclamation at all. She'd worked at Kitt Peak. Her name was Lynds, Lynds, and she married a guy of that name, but her name was Beverly, and she used the name. She died on the 5th of October this year at the age of 95. And I think she deserves a bit of credit for the wonderful work she's done. There's a massive catalogue of these dark nebulae. And, another person who's done a heap of work but has disappeared into obscurity and yet did all the footwork. And so some of the dark nebulae I'm going to point out to you, which are in Taurus, are actually ones that she mapped, but also ones that are a couple of spooky ones. A bit of a Halloween theme for later on. Okay, so let's have a look at what's up there. Uranus, Jupiter. These are pretty obvious in the night sky. So obviously in summer you're going to be treated to a bit of the planetary display. And over here on the far right, I'll point out the main constellations to you. Orion, Monoceros, the unicorn. And you can see this little double star here, Canis Minor, the little dog. The little dog always rides on the back of the unicorn. The unicorn is upside down. What is above the unicorn? What does Orion always take with him? The hunter. He has two dogs. The greater dog, Canis Major, is the one above. So what is the star in Canis Major that's really high up at the moment? Brightest star in the sky? Sirius, right, 8.5 light years away. You can't miss it. It's a blaring light. Down here you've got Gemini. Talking about exoplanets. Now that's a very interesting star system, a 6-star system. which I think I've referred to before. Before we get back to it though, Mars, you can see Mars there. So you're going to have a spectacular time in January looking at all these planets. But these two, Pollux and Castor, Pollux I think is about 34 light years away. Castor is a 6-sun system, 51 light years away, and it is spectacular. And there's a photo of a couple of the stars in it. It is 3 binary stars. And the last two, the third pair are 2 red dwarfs orbiting each other. Absolutely fascinating. So I love this system. There it is there.
So 6 stars and all.
Yes. And the complexity of it, the complexity of the system, you know, orbiting in this long, massive orbit like this. I forget the time period. It's quite substantial. But they're gravitationally bound. It's a proper sextuple star. But yeah, we'll show you another one later in a short time. Auriga. Now, nobody looks at the north and down low on the horizon except us when we do our astrophotography because the best targets, darn it, are so low at the moment. There are some gorgeous things. You can see a hint of red over here. This is the California Nebula. Auriga is what, by the way, following our theme today of Gladiator? The Charioteer. Auriga is the Charioteer. So, and in fact, Taurus ends, the horn of the bull, ends here on the star Elenath, and there's some fascinating stuff in this little zone I'm going to show you shortly. So we'll just move on. What else did I want to show you? Oh yes, okay, Perseus down there. The interesting thing is, some of these northern constellations like Andromeda, Pegasus, and a couple of others, the people are the right way up for us. So when they were drawn in the northern hemisphere, they must have been upside down, which is rather interesting, don't you think? Not with all of them, but just a few. I thought that was rather strange. Of course, you can see other interesting objects. The Hyades, Tennyson's Ulysses. The Hyades are associated with April rains in England and in Europe. And so when the rainy Hyades vexed the dim seas, remember this from Tennyson's beautiful poem, Ulysses, which is my favourite poem in the English language? No? Right? Well, the Hyades are the half-sisters of the Pleiades. And we all know the Pleiades means what in Japanese? Subaru, which I keep mentioning all the time. It is, and that's why they're on the bonnet of Subaru cars. So, it's true. There was a company, 5 companies, they got together and formed a big company, so hence 6 stars. But there are more than 6 stars, of course, in the Pleiades. 6 or 7, if you've got good eyesight, 7. Anyway, spectacular from the Midlands and any dark site. They are gorgeous to look at. Naked eye, forget the telescope. They're just brilliant to look at with the naked eye. Anyway, so we'll talk about those, not so much on those because we've talked about the Pleiades before. So let's look at Orion, because Orion has so much going for it. We all know this is, apart from Scorpius, this is the easily to recognise constellation with a lot of stuff going on. Things that we've photographed. If you look here carefully, you might just make out a funny little thing up there. I see 2118, which is... I'm waiting. The witch head nebula. And this star, which I'm going to, one of my favourite stars, I'll show you that in a moment. Regal, down here, Betelgeuse, which is going to blow any time. So they say. Could be 100,000 years, who knows? Could be longer. And down here, there's this big red patch, which you often see in shots of the galaxy, but it's actually part of the OB1 association, the big red gas cloud that goes right. You can see it here. This has all been part of, this is where a lot of these stars came from here. And in fact, when you look at their distances, they're all about 1,100 light years. So they all came from the same kind of area, the molecular cloud, same molecular cloud. So let's have a look at Regal. Now, Regal is gorgeous blue. And all you do is you get your telescope and you defocus the telescope. You defocus it on the star and you'll get a clear blue disk, and nothing is bluer than that. Maybe Spica or, I don't know, some other stars are comparably blue, but that is spectacular. And that is, of course, a quadruple star, 860 light years away. Supergiant B81A is its spectral class. And it's a massive star with a triple system. The triple system and the star make one revolution every 24,000 years. And it's quite weird, isn't it? And the actual triple system is, I think it's like 63 years for the stars to go around each other. there are 3 other stars. They're all B-class stars, all of them, and all massive, quite big. Anyway, what a fantastic system. That's 860 light years away, and of course Regal lights up the Witch Head. In fact, you wouldn't see the Witch Head without Regal, the light of Regal, because it's a reflection nebula. Over here is one of my, sorry, that's my old photo of the Horsehead. And of course, this spooky skull. Can you see the skull? Can't see it so clearly there. I always point out the skull. Anyway, moving on. And the flame nebula, or the sacred bush, which is where Moses got the 10 Commandments. You remember that? Yes, the story in the Bible. Anyway, they call it the sacred bush. Now, over here is the star Sigma Orionis, at least a quintuplet star. And in fact, these are, I'll just show you this. So ED, AB, and C. Now that's gigantic. That's huge. The first component is almost 18 solar masses. So it's a really big star. And the one next to it, I think they orbit in 10 days or something silly like that, very close. And there are more stars in the system, but they are at the heart of a beautiful cluster of stars. So when you think of Sigma Orionis, which, by the way, is there and lights up the Horsehead, without it, it wouldn't be nearly as bright, be not so visible. Over here on the right, you've got M78. Oh, sorry, a bit more about Sigma Orionis. So another quintuplet star. And this itself is a spectroscopic binary, so you can't see it through a telescope. You need a spectrograph to separate the light curves and the composition of the star, 2 stars. But huge, huge. So that's a massive system. In fact, there is nothing small about anything in Orion. For example, these 3 stars are all gigantic. They're all big, or at least bright giants. And they're all roughly the same. And of course, in Egyptian mythology, in Egyptian astronomy, they were the pyramids were aligned to them in exactly the same alignment. Cheops, Khufu, and Menkaure. And over here, if you look over here, sorry, I was going to come back to this again. I took this photo, which, as I said, got an underwhelming response. But that's my photo of M78, Casper the Friendly Ghost Nebula. Now, this has, I don't know how friendly it is, but it does have some very interesting things in it. It's very blue, so presence of oxygen, hydrogen. This bit here you see here is actually Barnard's Loop. So it's actually sitting on the edge of the inside edge of Barnard's Loop. It is a very small nebula, and I captured that with Big Bertha, or Beastie Boy as I call him, the 6-inch telescope I have, the refractor. Yeah, 8 minutes by 6 arc minutes, fairly faint, but and 10 light years across, so it's not a gigantic nebula by any means. And there's what did I do there? That's an APS-C sensor on the big telescope. That's what I used to frame it. That's been taken with a large telescope. But anyway, very pretty colours. I like things with pretty colours. Sorry to dwell on Orion, but there are other things to see. Look at what was really up there in Orion. So over here, you've got Mintaka, Alnilam, and Alnitak. Then you've got the Horsehead up here. You've got the Orion Nebula up here. And to the right of the Orion Nebula, just up the top of it, is a beautiful, beautiful cluster of stars. NGC 1980, also known as the tip of the sword, or the jewel in the sword of Orion. But anyway, we'll come back to that in a minute. I'll talk about that shortly. There's that big nebula at the bottom, the Lambda Centauri and Lambda Orionis Nebula. The head of Orion is right in the middle of all this. And there is Betelgeuse, of course, and Bellatrix. Up here is Saiph, S-A-I-P-H, and of course Regal again. And there's the Witch Head. Now that spectacular picture was taken by, don't look at me because it wasn't me. Anyone know? Greg, our master photographer. That is on the TestStar website. If you want to see it, if you've ever seen it before, it should be an APOD winner. It is just absolutely, when you see it on the screen, it is stunning, absolutely stunning. Best Witch Head photo I've ever seen anywhere, including Hubble and all the rest. Yeah, not a patch. This is brilliant. And it's just, when you look at it, it's smoky. It's got this, it's like a puff of smoke rather than just it's a really gorgeous thing to look at. Anyway, so now down here, another shot, again, I took a long time ago, of the Horsehead, and that a nuisance star, on attack, is always ruining our photos. Here it is again, compared to the sun. So you can see what a giant star it is. Not as big as some giant stars, but big enough. And of course, the light of it does suffuse all the photos, and you have to use these narrowband filters, and you're going like mad trying to dim the light from it, but it doesn't always work, unfortunately. So moving on. Picture of the Orion Nebula I took with an optical angle extreme. What do you notice? Very few stars. So when you use red light filters, of course, you diminish the size and number of stars. But if you look up here, this is what I want to look at. That's what I was telling you about. Look, this gorgeous cluster. Now I'll show you what it really looks like. Isn't that beautiful? If you have a reflected telescope, you'll always take better photos of star clusters because they've got these lovely spikes. Some people don't like diffraction spikes, but I love them on star clusters. You can't get anything better. Isn't that gorgeous? So the jewel in Orion or something, I think the Arabic term for that was, a really beautiful thing. The lost jewel of Orion, sorry, lost jewel. Now, here it is here. This is a frame looking through an eyepiece, Teleview 24mm. Magnification here is 34 times. That's roughly what you'd get. My microphone's still going? Yeah. Okay, so let's move on. Very, very pretty. Now look at this. Now this was taken by Greg, of course. And it's a spectacular, I have never seen anything as good as that, including, yeah, it's a dual panel. Now, I haven't seen, even Rigel Bernal Andreo's photos aren't as good as that in my opinion. I think that's better. And that's from the Horsehead all the way to the Orion Nebula on the right. And look at it, and look at the mark. He's such a modest guy, but he takes the most amazing shots. So recently we were at Mount Pleasant, there was smoke in the air, Andromeda was 1 degree above the horizon, or 2 degrees, something ridiculous, looking through all that pea soup atmosphere, and he took the most spectacular photograph. It's just unbelievable what he does. So he's very good at extracting. Oh, you can clearly see 3 of the stars in Sigma Orionis up here. In fact, you can see 4 in the system. And by the way, that system spreads up to 16 arc seconds, those 5 stars, quite wide. Oh, sorry to keep going back to Orion. We will get off Orion in a minute, but there's just a couple more things I want to show you. Remember this little patch here. Now, don't forget, the star cursor belongs to Eridanus. That's Eridanus on the top left there. And look over here in this little area, and you'll see a nebula called the Cosmic Bat, or the Fox-Face Nebula. Now, as it turned out, after our discussions today, we've established there is not 1, but 2. There are 2 Cosmic Bat nebulas. This is the lesser one. Eugene reckons there's no damn bat there at all. And I'm probably inclined to agree. But then I saw a video on the internet zooming in on this, and it looked like a couple of ears, and I thought, yeah, stretching it a bit. Cosmic Bat maybe. But anyway, that thing is, it's there if you want to have a look at it. An interesting thing. Here's the whole object framed with Astro Boy, my astrophysics refractor, using APS-C size sensor. So you'd fit the whole. So the bit that you're looking at there is the end bit here, okay? NGC 1616, whatever it is. Now, oh, sorry about the gizmo there. Down there is the Monkey Head Nebula, which I have to photograph shortly, I hope. In probably narrowband. It's an emission nebula, so you would photograph it in narrowband. There's the monkey. There's the monkey head. Look, baboon. Hey, didn't we see baboons today? Look, here's a baboon. Here's a mouth, head, and it's sitting there. Unlike the baboons in Gladiator 2, this is a big space. I don't know what they mean by retired. They shoot it down. They decommissioned it, but the Spitzer was a brilliant. Sorry. The Spitzer telescope had took the most fantastic image of the Horsehead I've ever seen. Have you ever seen that close up of the horse? It was beautiful. And just, I don't know what they did with it. A bit sad, a bit like Cassini's fate, Those faithful instruments, and they ruin them or do something to them. Anyway, here is the real bat. Look at that. Now that looks like a bat coming at you. I thought I'd give you a Halloween, this looks like a batarang actually. LDN 43. Now I saw a site today referring to that LDN by a different number. So there are inaccuracies. Don't trust Wikipedia all the time. But there are discrepancies in some of the names of these objects. So, but isn't that creepy? Can everyone see the bat? Now that's one I'm going to definitely take a picture of. Look at it's just beautiful, but yeah, I think it's fairly small from memory. I think it's rather small. Because I clipped this out of to find where it was. So this is the head of the scorpion. We'll recognise the Schubafang up here, Eclil. One of those is Eclil. Down here, now what's this object? 4592, famous. Sorry? Blue Horsehead Nebula. Yeah, this is the Blue Horsehead. This is another gorgeous nebula. And over here, not far away, is where this is located. Yeah. Back to Taurus now. Leave Orion for a bit. Let's look at Taurus. In case you want to know how the bull is positioned from northern, relative to us, of course, it's upside down. Look at all the dark nebulae in this area. Taurus is just full of these very interesting objects. Probably more than a lot of other constellations. So if you look in this general direction. Now, being a lover of Latin, you've got the Hyades here. Prima Hyundum, the first Hyades. Secunda, the second. Tertia, Hyundum Tertia, Latin for third. Third of the Hyades. And of course, Ain is the right eye of the bull, supposed to be the right eye of the bull, and Aldebaran. And that is a massive star, and it has a planet, exoplanet. Discovered. A massive multi-Jupiter, multi-time size, several times the size of Jupiter. Big planet, big gas giant. So there you go, Ain. Anyway, right. So the Hyades down up, Pleiades down there. So if you see Hyades, look for the Pleiades. They're always close to each other. Now down here at the bottom is LDN 1489. Sorry. I'll come back to that. That's suddenly appeared. It shouldn't have been there. Go away. The Pleiades, gorgeous to photograph. Look through the telescope, look through binoculars. A wide group of stars. Beautiful. And if you've got binoculars, you'll probably pick up the nebulosity because they're so bright. The nebulosity, of course, it's a reflection. It's only reflected light from those stars that have moved into it. They've all got the same directional velocity. They've all been born out of the same cloud, so we know they were born in the same space. And they're just happily drifting along. This is what I love about the galaxy. You've got these travellers. Rogue planets, rogue stars, and then groups of stars travelling together like families. This is about 444 light years away, and it's going to, this is the closest star cluster to us, open cluster, the Hyades, and this is, I think, number 2 or number 3, I'm not sure, I'm trying to remember what the other one was. Anyway, so C41, the Hyades. Sorry about the arrows and gizmos. Interesting little cluster up there, the Pirate Moon cluster, for those who are interested. Have you looked at it? No, have you looked at that, Steve? Because yeah, Pirate Moon. And over here is a nice little diagram, what it looks like through an eyepiece at 41 magnifications. So, which is low, and that's what you want. A beautiful, gorgeous sight. Now, down here, the LDNs, 1495, what is it? Well, it's an interesting, you probably can't see it up there. Sorry, it's pretty small. I didn't think about that. I should have put separate slides for some of these. It's got a lovely bit of blue in it and a gorgeous arc of dark material. That might be worth taking a photo of. It's pretty small. What's the field there? Yeah, oh no, it's 1 degree across, 1.5 degrees across. Now, down here is an even more interesting one. It looks like the head of a parrot, another dark nebula. Look at the interesting, can you see that from the back? Yeah. So you've got eye and a beak. You saw that in the NGC 2014, didn't you? Remember the bird? You said it was a bird. The one of the Dragon's Head Nebula. Yeah, Dragon's Head. Okay. Chicken head. Chicken head. Okay, so there you go. So again, the same sort of field of view, quite a decent size, but because they're faint, long exposure photography if you're doing photography. So for those of you interested, there's several hours probably to expose some of these. A close-up look at the Hyades just for a moment. A beautiful thing to look at. There's a photograph. I don't know who took that photograph, but it's a gorgeous cluster of stars. The main ones are in this group here, all quite large stars. Aldebaran is not. Aldebaran's something like 67 light years away or something. It has nothing to do with these, with this group, which are twice that distance, 130 something light years. But beautiful. So worth staring at through our binoculars, I think, or low magnification in a telescope. Now, Auriga, down low on the horizon, where we curse the smoke and the dense atmosphere and the planes travelling along, as we often get at Mount Pleasant, you know, while we're taking photos and eating party pies. And as we're going along, if you look here, you can see interesting smudges and things. This is a gorgeous area. Oh, just this is the stuff of dreams. Now, if only it was a bit higher. On the left, the Flaming Star Nebula. Look at it. This is beautiful. Of course, Greg has taken a spectacular image of it, which I haven't got here tonight. But this field is so interesting. Look at it through binoculars. Get an eye full of Auriga. Look, there's a shot. I think Greg's is better than that. That's on the internet. This is mesmerising. And look over here. You can see, look, these two clusters, M36 and M38, which I'm going to talk about briefly, and that gorgeous thing there, which is a spider. Yeah. So the Flaming Star Nebula, that nebula, the tadpoles, and the letter Y cluster. And if you look in the middle, you can see a 1, 2, 3. Can you see that? Letter Y. No? No? Sorry about that. But anyway, worth looking at. Now over here is a close-up of that cluster on the right there, M36, gorgeous. Look at the blue in that pinwheel cluster, and then to the left, the M38. Now they are, have you looked through that, seen those, Steve? They're very, very pretty and worth looking at through a telescope or binocular. So again, get your binocs out, because your binoculars will always deliver spectacular views, wide field views, and that's what you want for this area. And you pick up these little knots of light, these beautiful clusters, which aren't as big as, say, 3532, what is it? Football cluster, wishing well cluster, but still big enough. And here's the spider up here, IC417. Oh, sorry, I went a bit fast there. For those of you who want, you can see it's an emission nebula being red, a big star field. I forget who took that. What was that? Mount Vernon? No, I can't read that, sorry. I should acknowledge it. But anyway, wow, that's another one, huge target, hydrogen alpha. Now, just quickly, over here, look at this. Look at this. Look at it. CMAS 147 or Sharpless 2240 Spaghetti Nebula. Now, this guy got the APOD photo, astronomy photo of the day from NASA for this photo. And there's another one that's even better, which is close up that he's taken. That is just amazing. And there's another shot by another guy, also got an APOD for it. Now, that's the Spaghetti Nebula. Now, I've got to tell you, this is about 3 degrees across. So this needs a panel mosaic shot, you know, several shots. But it's right next to the star Elnath, which you remember is the last star on the right horn of the bull. Okay, quite bright, about magnitude 2 or 3, something like that. Sorry? Yeah, it is better than the Flaming Star. It's got a bit more elevation. Yes, we all look. That's our next target. Anyway, it looks spectacular and reminds me of the one I took, the supernova remnant, you know, the lovely red and blue. So, yeah, so a narrow band, hydrogen alpha and oxygen 3, and man, smoking. It would look really good. Anyway, moving on. So there you go. Now, Canis Major, Monoceros and Cancer on the right. Just as a wide field view, just a couple of things I wanted to say to you about that. Up the top is a beautiful M41 little beehive cluster, which is right here in the heart of the dog. And down here, oops, that's moved a bit. It should be on there. How did that move? I must have done something to it. Now, Eugen, do you recognise your photo? This is Eugen's wonderful photo of the Seagull Nebula, which is right there on the boundary of Monoceros and Canis Major, but belongs to Monoceros. Isn't that gorgeous? Beautiful on a big screen, and lovely, just lovely. So, Eugen, there you go. Well done. Now, the Seagull Nebula, glowing lights, gorgeous. A wonderful target, and I think it's about 130, 140 light years long. So it's quite spectacular. And you can do that. You can image that narrowband. Yeah, it's worth looking at. There's a shot of mine of the Rosette Nebula, which is the one down the bottom there. Here, and there's one more to go. 2264, which some of you will remember, and we're going to star Eugen in this. No, that's in Canis Major. Christmas tree. Well done, well done. So here we go. That last one, I've got it right here. Ta-da! Eugen again. Now I love this. Oh, sorry. Am I still on? Yes, good. Okay. So this is Eugen's beautiful photo. I've stretched it to the whole screen, Eugen. Sorry for a bit of distortion there, but this is a gorgeous. Look at this. This is the Cone Nebula, right? And if you look down here, this is the base of a tree, and its base is the crown of the tree is across that way. It goes up like that. It's a Christmas tree. Can you see the triangle? Well, that's called the Christmas tree cluster. Beautiful. That star is a Corker, that one there. Look how bright it is. And down here, if you look carefully, you can see the Fox-Fir Nebula. Yeah. So this is wide field, but I love this photo because the colours, the composition, everything about it, it's just smoking good. 420, so fairly wide. 4 degrees, 5 degrees maybe. It's quite wide, yeah. And moving east doesn't look boring in the east. There's not much happening, but there are a couple of interesting things down here. Firstly, the beautiful, beautiful beehive cluster in Cancer, or Praesepe, as it's also known. Look, when you look at that through binoculars, it's gorgeous, gorgeous to look at. And you can see it's clearly got a lot of red giants and blue stars, young stars. And down here is a view of it at a magnification of just 20 times, 21 times. So a pair of binoculars would deliver a very similar view, a good view, 7 by 50, 7 magnifications. Wouldn't be as big, obviously, but would still be very pretty and quite bright, super bright. Okay, so not all is lost in the east. Let's turn to the south. Now, you all know that by now the Southern Cross has swung, it's crossed the meridian on its lowest path and is rising up in the east. And so all those gorgeous star clusters and things that we all have been talking about for years are there for you to see. I'm going to show you a couple of things here that are worth looking at. You already know this one, the jewel box. Don't forget the jewel box. Don't forget this one, 3766. Anyone know? Pearl cluster. Very pretty. They reckon a competitor for this too. And over here, the running chicken. I put it crossways to show you that it is a chicken bending down. You can see its beak. Now, I filmed that in normal light, but I've also got it in hydrogen, oxygen palette. I haven't got that here today, so I won't show you that. And that's my picture of one of the most beautiful things you'll ever see in the night sky. Once again, apart from the Sprinter cluster, there is this one. Now, this is the Wishing Well cluster, or Diamond cluster, or Black Arrow cluster. It's got about 5 names. Spectacular. When you look through a telescope, you don't see any of that colour, but you just see this dazzling, dazzling central group of stars, like looking through clear water at a shimmering, just amazing. Take your breath away. Gorgeous. So that's 3532 for those of you who want to put that down for your telescope. And here we have my, the Statue of Liberty. Now that's, I think it's 3603 or something, this nebula. Has nothing to do with that. This one is 20,000 light years away. And this one is in the foreground at 9,000 light years away. Both are mission nebulae, but the one in the background is the biggest one in the galaxy, apparently. I read somewhere. and it looks gigantic, and you can't see it here, but if you've got a high magnification here, there are some super massive Wolf-Rayet stars and O-class stars in the middle of that. So quite spectacular. And up here is one of my favourites, Edeka and I always say when I look through, I love looking along here with the starfire. This just fascinates me. If you get in there observing and look at these massive pillars of dark nebulosity through a telescope, it's bright and it's wonderful to look at. Yeah, gorgeous, gorgeous. Now, finally, to the west. Not all is lost. As soon as you see the word sculptor, you know you're in galaxies, wading through galaxies. This is the NGC 300, also known as the, well, its proper name is just NGC 300, but Sculptor Pinwheel is its proper name. Gorgeous, isn't it? Red nebulosity. Another one to photograph. Down here next to it, these are all these are closer to us than you think, a lot of them. I think 300 is part of the local group. 55 is the string of pearls. That is really big, like past moon size, full moon size. So if you take a photo, it doesn't take you long to get a decent image. And if through a pair of binoculars, it'd be a bright smudge, quite bright. So there's another one that's worth looking at. In the west, the String of Pearls Galaxy. And over here, of course, is one of my favourites, 253, the Silver Dollar Galaxy, or the Sculptor Galaxy, as it's commonly known. And I took that picture with a 4-inch telescope. So you can take it, even a small telescope, it's so bright, there's so much in there. And that's the middle of the picture. I've cropped it, obviously, but if you saw the original, it's pretty small. Anyway, Sculptor Galaxy, Silver Dollar. Now down here is Saturn. What a feast! Saturn, Jupiter, Mars, Uranus. You've got them all. And somewhere in there's probably Neptune, but I didn't find out. Oh, there it is. Yeah, yeah, be close. Yeah, down here.
These ones, the last one, you want to see all the planets in one night.
Yeah.
Now's the time to do it.
Yeah.
They are, it's a parade.
Yeah. There you go. Challenge.
Yeah, clouds.
Yeah, I know. And finally, I think a little cartoon.
That's very
I know, Larson, I can't escape him. But I did want to show you something, if I can, before I completely finish. I've got a picture here somewhere. I'll go to, I've got no internet. Is it gone, is it? Oh, rats. I was going to show you a picture of Beverly Lind, who I was talking about earlier, in the dark nebula. And she's got this wonderful photo of her. She's 95. And she's standing there in a T-shirt with a picture of the James Webb telescope she's taken. The whole T-shirt is a print of of all these galaxies in there. I think it's the most wonderful thing, you know, to see that in a person still sparkling with life. So anyway, so next time you think of dark nebula, I think of Beverly Lind. Yeah. All right, thanks, folks. Thank you. Lights.
Just a couple of announcements. Greg England, who took a lot of photos, is selling his ATQ5 for $1,050, costing him $2,500. Got a belt drive.
You in the market for it?
You in the market for it? So he's advertised it on Astro Imaging Tasmania, so $1,050. So it's hardly ever used. And the other thing is, Saturday there's a members observing night at Mount Pleasant, but it looks like cloud and rain. So
Yeah, it will.
I'll go out for an hour or so if anyone wants to.
And my apologies for the bad weather. I bought a new telescope, and that's what you get as soon as. It's all my fault. By the way, just a little reminder: some of you are coming out tomorrow night to Girl Guides at the Lee. Thank you. Thanks, guys. Anyone else who wants to bring along, if you've got your Working with Vulnerable People card, I'm doing a talk to the Girl Guides there, and then we're going to hopefully see some sky. I don't think so. sorry, it's up the lee, but the upper part. I know, hence my talk. Yeah.
Quick thing, some new places in here. So, Southwest Sky Country, Dark Sky Country. Brochures and information if anybody's interested to learn about what's happening down there. On the table, on the way out.
Thanks, folks. Thank you.
Thank you.